In the summer of 1969, the United States Navy conducted a classified strategic assessment of Soviet long-range naval aviation. The analysis was blunt. The current generation of Soviet bombers, primarily the subsonic Tupolev Tu-16 and the marginally supersonic Tu-22, posed a manageable threat to American carrier battle groups operating in the North Atlantic. American surface-to-air missile batteries and the combat air patrols, maintained by carrier-based fighters, could intercept these aircraft before they achieved a viable weapons release position. For the admirals in Washington, the calculus was uncomfortable but controllable. For the commanders of Soviet naval aviation, reading those same strategic assessments through their own intelligence channels, it was an unacceptable vulnerability. The carrier battle group was the centerpiece of American power projection. By 1970, the United States Navy operated 15 nuclear-powered and conventionally powered carriers, each capable of projecting decisive air power across hundreds of kilometers of open ocean. In the event of a conventional conflict in the North Atlantic or the Mediterranean, these carrier groups would be the decisive instrument. To the Soviet High Command, they represented an existential threat that had to be neutralized at the outset of any conflict. The math was direct. If American carriers could operate with impunity, Soviet surface forces, the Northern Fleet, and the strategic missile submarines sheltering in their bastions beneath the Arctic ice were all at risk. The answer seemed obvious: build a better bomber. But the Soviet Union had been building bombers for decades, and the result was a fleet that American planners were confident they could handle. The problem was not industrial capacity or political willpower. It was physics. To destroy a carrier battle group, a bomber had to survive long enough to get within weapons release range. American carrier air wings flew combat air patrols hundreds of kilometers from the ship. American surface combatants carried the Terrier and later the Standard surface-to-air missile, capable of engaging targets at long range. Any aircraft slow enough to track reliably on radar was slow enough to kill. The mandate handed down from Moscow to the Tupolev Design Bureau was therefore not simply to design a new bomber. It was to design a bomber that could make the entire defensive architecture of a carrier battle group mathematically irrelevant. That mandate would produce one of the most technically sophisticated and strategically alarming aircraft of the Cold War. A machine so deeply disturbing to American military planners that it fundamentally restructured carrier air wing doctrine, drove the development of an entirely new class of fleet defense fighter, and ignited one of the most bitter diplomatic disputes of the SALT era. The West called it the Backfire. The Soviets called it the Tu-22M. And for nearly 2 decades, the precise capability of this aircraft remained the single most debated question in the entire strategic arms control process. If the hidden engineering decisions and classified diplomatic battles that shaped Cold War military history compel you, I invite you to subscribe as we reconstruct these declassified programs with the technical precision they deserve. To understand why the Tu-22M was so alarming, you first have to understand the specific physical problem the Tupolev engineers were assigned to solve. Shooting down an aircraft at high altitude with a surface-to-air missile in the early 1970s was an increasingly reliable proposition. The combat experience of the Vietnam War and the Arab-Israeli conflicts had demonstrated that modern radar-guided missiles could intercept aircraft flying predictable, straight and level profiles at medium and high altitudes with considerable reliability. The tactical response adopted by Western air forces was to fly lower below the radar horizon, using terrain masking and the curvature of the Earth to approach targets undetected before the defending systems had time to react. But penetrating at low altitude carried its own severe aerodynamic penalty. At sea level, atmospheric air density is roughly twice what it is at 10,000 meters of altitude. A jet aircraft flying fast at sea level encounters dramatically greater aerodynamic drag. The structural stress loaded into the airframe increases exponentially with both speed and air density. Fuel consumption spikes. The time available for a defending fighter crew to react to an inbound threat compresses from minutes to seconds. And for a heavy bomber, those constraints created a brutal engineering paradox. To survive long enough to release its weapons, the aircraft had to fly fast and low. But flying fast and low at any useful range required fuel quantities that exceeded the practical limits of an aircraft already carrying a heavy weapons load. and a bomber with insufficient range could not reach the target sets it was designed to destroy. The Tupolev engineers were staring at a set of requirements that directly contradicted one another. The aircraft had to carry a meaningful payload of standoff weapons. It had to possess the range to reach carrier battle groups operating deep in the Norwegian Sea and the North Atlantic. It had to be fast enough at low altitude to outpace intercepting fighters and outrun the engagement envelopes of shipboard surface-to-air missile systems. And it had to be structurally robust enough to sustain supersonic flight at altitudes where the atmospheric battering would destroy a conventional airframe within minutes. Every parameter demanded by the military requirement pulled against every other parameter in a different direction. The initial design review within the Tupolev Bureau confirmed a fundamental incompatibility between these requirements and any fixed geometry wing configuration. A conventional swept wing optimized for high-speed supersonic flight generates insufficient lift at the lower airspeeds required for takeoff and landing from Soviet military airfields. A wing optimized for low-speed performance creates catastrophic aerodynamic drag the moment the aircraft attempts to push past Mach 1. The chief designers understood they were facing a hard aerodynamic boundary that no fixed planform could cross. The only viable solution was one that American and European aerospace engineers had been simultaneously investigating with comparable intensity. The variable geometry wing, or swing wing, was an engineering concept theorized for decades, but only recently achievable, given advances in titanium metallurgy and high-pressure hydraulic actuation. The fundamental principle of variable geometry is elegant in its logic. At low airspeeds, the wings are swept fully forward, presenting a large surface area to generate the high lift coefficients required for takeoff, landing, and subsonic cruise. As the aircraft accelerates and the aerodynamic environment changes, powerful hydraulic actuators pivot the entire outer wing panel rearward along a massive central hinge point. At maximum sweep, the wings fold back to a sharply acute angle, dramatically reducing the frontal cross-section that the rushing air must flow around, minimizing drag, and allowing the aircraft to achieve sustained supersonic performance. The aerodynamic theory was sound. The engineering implementation was extraordinarily demanding. The central pivot mechanism required to sweep wings carrying the full aerodynamic loads of a heavy bomber weighing tens of thousands of kilograms is a component of staggering mechanical complexity. At supersonic speeds, the forces acting on a swept wing are not gentle. They are massive, continuously shifting torsional loads that attempt to twist, bend, and shear the pivot structure with every variation in atmospheric turbulence. The pivot housing had to be machined from high-grade titanium alloy, capable of resisting both the mechanical loads and the severe thermal stress generated by aerodynamic heating during prolonged high-speed flight at low altitude. The hydraulic actuators driving the sweep mechanism had to operate with absolute precision under conditions of extreme vibration and temperature variation. If the pivot mechanism failed asymmetrically, sweeping one wing while the other remained fixed, the resulting differential aerodynamic force would tear the aircraft apart in a fraction of a second. Furthermore, as the wings swept backward, the aerodynamic center of pressure shifted dramatically relative to the aircraft's center of gravity. On a fixed-wing aircraft, this relationship is managed by the careful design of the horizontal tail surfaces. But on a variable geometry platform, the pilot is essentially flying a fundamentally different aerodynamic machine at each sweep angle. The pitch stability, the roll response, and the yaw authority all shift as the wings move through their arc. The flight control system had to be engineered to compensate for these constantly changing aerodynamic characteristics, automatically adjusting control surface deflections to maintain stable, controllable flight throughout the full range of wing positions. This was a software and control engineering problem of immense sophistication, given the computing technology available in the early 1970s. The Tupolev engineers spent years running scale models through the wind tunnels of the Central Aero Hydrodynamic Institute at Zhukovsky, methodically mapping the aerodynamic behavior of the swing wing configuration at every combination of speed, altitude, and sweep angle. The data confirmed the performance potential of the design and simultaneously revealed a catalog of aerodynamic instabilities and destructive flutter modes that had to be individually suppressed through painstaking geometric refinement. The sweep mechanism went through multiple full-scale ground test campaigns, with prototype pivot housings deliberately loaded to several times their anticipated flight loads to verify structural integrity before a single complete airframe was assembled. Put yourself in the position of a NATO intelligence analyst receiving the first fragmentary reports of this program in the early 1970s. The Soviet Union already operated some designs incorporating swing-wing technology, most notably the Su-17 tactical strike aircraft. But those were small, single-engine platforms. The signals intelligence and human source reporting now accumulating suggested that the Tupolev Bureau was applying the variable geometry principle to a full-scale supersonic maritime strike bomber. The sheer ambition of the undertaking was difficult to credit. American experience with the F-111, the Western world's most advanced swing-wing aircraft, had demonstrated how mechanically complex and maintenance-intensive the variable geometry system was, even when backed by the full industrial capacity of the United States aerospace industry. The idea that the Soviet aviation industry could successfully field a heavy supersonic bomber incorporating these systems at operational scale seemed, to many analysts, technically implausible. They were wrong. The first prototype flew in 1969. The definitive production variant, the Tu-22M that entered frontline service with Soviet naval aviation and long-range aviation in the early 1980s, was a machine whose performance specifications, when they were finally assembled by Western intelligence into a coherent picture, triggered immediate alarm at every level of NATO command. The aircraft was powered by two Kuznetsov NK-25 afterburning turbofan engines, each producing over 245 kilonewtons of thrust with afterburners engaged. At high altitude, the Tu-22M was capable of Mach 1.88. But that high altitude figure, while impressive, was not the performance parameter that kept American naval planners awake at night. The critical number was its low altitude supersonic dash capability. At sea level, in the dense air where both surface-to-air missiles and carrier-based fighters had to engage it, the Tu-22M could sustain speeds approaching Mach 1. It could cover over 1,000 kilometers flying fast and low, well below the radar horizon of the battle group's surface ships, before climbing to weapons release altitude and turning for home. The weapons that aircraft carried made this speed profile strategically decisive. The primary armament for the anti-shipping mission was the KH-22 cruise missile, designated by NATO as the AS-4 Kitchen. This was not an anti-ship weapon in the manner of the French Exocet or the American Harpoon. The KOS-22 was nearly 12 meters long and weighed close to 6,000 kilograms fully fueled. It carried either a 1,000 kilogram conventional warhead or, in its primary operational configuration, a nuclear device with a yield estimated by Western intelligence at somewhere between 200 kilotons and 1 megaton. It flew at speeds exceeding Mach 4 on a semi-ballistic trajectory, climbing to over 25,000 meters at the apex of its flight path before diving almost vertically onto its target. Consider what that missile profile meant for the defensive systems of a carrier battle group. A Mach 4 weapon diving from 25,000 meters presents an engagement geometry that fundamentally overwhelms the design assumptions of most surface-to-air missile systems of that era. The terminal descent angle is nearly vertical. The window during which a defending system has both a valid tracking solution and the kinematic energy to reach the incoming weapon is not measured in minutes. It is measured in seconds, and a single Tu-22M is not the scenario. A full regiment operating in coordinated strike packages, using electronic jamming and deceptive routing to fragment the battle group's air picture, could place simultaneous inbound threats on multiple vectors against a defended formation that had already committed its interceptors in one direction. American carrier, air wing planners ran the intercept geometries relentlessly through the late 1970s and early 1980s. The F-4 Phantom, the standard fleet defense fighter of that era, had a combat air patrol radius and missile engagement envelope theoretically adequate against the older subsonic Tu-16 Badger. Against a Tu-22M executing a low-altitude dash at high subsonic speed, the intercept geometry was deeply unfavorable. The F-4 required precise positioning at exactly the right range, altitude, and vector, well in advance of the bomber's approach, to achieve a firing solution with its AIM-7 Sparrow radar-guided missiles. The compressed detection timeline at low altitude, where the radar horizon of a surface ship might give only minutes of warning, made this demanding task dramatically harder. The United States Navy's response was decisive and expensive. The F-14 Tomcat, which had been in development since the late 1960s as a replacement for the canceled F-111B Fleet Defense Program, was restructured and accelerated specifically to counter the Tu-22M threat profile. The Tomcat's own variable geometry wing, a direct aerodynamic parallel to the Soviet aircraft it was designed to intercept, gave it the high-speed dash performance needed to reach firing range before the Tu-22M could release its KH-22 missiles. The AWG-9 weapons control system, the most sophisticated airborne radar in the Western inventory, and the AIM-54 Phoenix gave the F-14 a long-range engagement capability that could theoretically target a Tu-22M at ranges exceeding 150 kilometers before the bomber had reached its own launch parameters. The AIM-54 Phoenix was the most expensive air-to-air missile in American service. Each F-14 could carry 6 of them simultaneously. The economics of this response were, in themselves, a revealing measure of how seriously the Tu-22M threat was taken. The Navy was committing enormous financial and industrial resources to a specific aircraft and a specific missile, whose entire design rationale was the ability to intercept one class of Soviet bomber before it could fire. The Tu-22M had forced a fundamental reorganization of carrier air wing doctrine simply by existing. The aircraft's operational implications did not stop at the boundaries of carrier aviation. The range performance of the Tu-22M, particularly when combined with the Soviet Union's capacity for aerial refueling, generated a strategic debate that penetrated the highest levels of arms control diplomacy. When American negotiators sat down with their Soviet counterparts to negotiate the SALT II Treaty in the mid-1970s, the Tu-22M immediately became the most contentious single aircraft type on the table. The American position was direct. The Tu-22M, with its demonstrated unrefueled range and its confirmed aerial refueling capability, was capable of conducting one-way strike missions against targets in the continental United States, if launched from bases on the Soviet Arctic coastline. By that definition, it was an intercontinental strategic delivery system and subject to SALT limits on strategic offensive arms. The Soviet position was equally firm in the opposite direction. The Tu-22M was officially designated a medium-range bomber intended for theater operations in Europe and against naval targets in adjacent seas. It was not an intercontinental system. It did not belong in the SALT counting rules. The Soviets pointed out, with some technical justification, that the aircraft, in its standard unrefueled configuration, did not possess the practical range for a meaningful round-trip strike mission against American interior targets. Both positions contained elements of genuine technical validity. The range arguments depended on assumptions about flight profiles, weapons loads, and basing locations that were themselves classified. American intelligence had reconstructed portions of the performance envelope through signals intelligence and the testimony of Soviet aviation defectors, but critical gaps remained. Soviet negotiators exploited those gaps with considerable diplomatic skill, insisting that the American characterization of the Tu-22M as a strategic system was a politically motivated attempt to constrain a conventional theater weapon. The negotiations extended for years. When SALT II was finally signed in Vienna in June 1979, the Tu-22M occupied an uncomfortable diplomatic limbo. The Soviets agreed as a separate political commitment to limit the number of aircraft configured with aerial refueling probes, directly addressing the American range concern. But the aircraft was not formally counted under the strategic bomber limits themselves. It was a significant concession by the American side, driven by the political imperative to conclude the treaty. The Tu-22M had successfully navigated the most intensive strategic arms control process of the Cold War and emerged essentially unconstrained. By the early 1980s, production Tu-22M aircraft were flowing from the Kazan aviation plant to operational units at a steady rate. At peak production, the fleet would eventually reach over 400 operational examples, distributed across long-range aviation and naval aviation regiments. The training infrastructure to support the platform was substantial. Aircrews had to master not only the demanding variable geometry aerodynamics of the aircraft itself, but also the complex sensor integration, missile employment procedures for the KH-22 system, electronic warfare protocols, and the intricate formation discipline required for coordinated multi-aircraft strike packages against defended naval targets. The men who flew these aircraft were an elite within Soviet aviation. The low-altitude supersonic dash profile was physiologically severe. At speeds approaching Mach 1 at sea level, the cockpit environment subjected crews to high-frequency airframe vibration, elevated noise levels, and the constant possibility that a bird strike at those velocities was a potentially fatal event. The aircraft required 4 crew members: pilot, co-pilot, navigator, and weapons systems operator. On extended maritime patrol missions, probing the edges of NATO's detection networks in the Norwegian Sea, crews operated for hours in this demanding environment, maintaining the situational awareness required by an aircraft that, if it descended to its attack profile and accelerated to dash speed, was operating at the edge of its structural envelope. The operational deployment patterns of the Tu-22M force in the early 1980s were tracked with intense interest by American and NATO intelligence. When regiments conducted maritime strike exercises in the Norwegian Sea, simulating coordinated multi-aircraft attacks against carrier battlegroup coordinates, American carriers in the region adjusted their defensive postures, rotating additional F-14s into combat air patrol stations and activating the full defensive suites of their surface escort vessels. The exercises demonstrated in practical terms the challenge of coordinating a carrier battle group's defense against a determined strike by a supersonic bomber force even under peacetime exercise conditions, when the outcome carried no real consequences. The maintenance footprint of the Tu-22M fleet proved, over time, to be one of its most significant operational limitations. The variable geometry pivot mechanism, that masterpiece of titanium engineering at the heart of the aircraft's performance, required intensive, scheduled inspection intervals. The hydraulic systems driving the sweep actuators operated under extreme pressures and were susceptible to fluid leaks that could degrade the precision of wing positioning. The NK-25 engines had relatively short time between overhaul intervals that kept the maintenance facilities at Soviet air bases working at maximum capacity. The electronic systems, particularly the attack radar and the electronic warfare suites, carried in various configurations, required specialized ground support equipment and highly trained technicians whose skills were difficult to develop and retain at the scale of the force. When the Soviet Union dissolved on December 25, 1991, the Tu-22M fleet was divided among the successor states. Russia retained the majority of the operational aircraft. Ukraine inherited a substantial number based on its territory and eventually scrapped most of them through arms reduction agreements in the 1990s, funded in part by Western non-proliferation programs. The same international financial architecture that was simultaneously paying to dismantle the Typhoon-class submarines in Severodvinsk was purchasing the elimination of the Tu-22M force that had once threatened to destroy the carrier groups those submarines depended on to survive. The Russian Federation's remaining Tu-22M fleet entered the post-Soviet period in a state of severe operational degradation. Maintenance funding collapsed. Aircraft were grounded for months at a time awaiting spare parts. Crews flew at a fraction of the training hours required to maintain proficiency in the demanding low-altitude attack profile that was the aircraft's entire tactical purpose. The vast logistical infrastructure that had sustained the fleet through the 1980s disintegrated alongside the economic system that had built it. For years, the aircraft that had forced an entire restructuring of American carrier air wing doctrine sat idle on concrete ramps in the Russian interior, slowly deteriorating. Russia eventually stabilized the fleet and restored some level of operational capability as its economic position improved in the early 2000s. The Tu-22M flew in combat operations over Chechnya, and later in the 2008 war in Georgia, though primarily in high-altitude conventional strike roles that bore little resemblance to the terrifying low-altitude nuclear attack mission the aircraft had been engineered to execute. The combat employment of this machine against ground targets using unguided conventional bombs was a striking diminishment for an aircraft that had once been considered the most dangerous threat to the survivability of an American carrier battle group. Looking at the full arc of the Tu-22M3's operational history, what emerges is a picture of extraordinary technical achievement in service of a strategic purpose that was never tested in practice. From a purely aeronautical standpoint, the Tupolev Bureau's accomplishment was formidable. They designed, manufactured, and sustained in operational service a variable geometry supersonic maritime strike bomber at a scale that no nation outside the United States ever attempted. The pivot mechanism that NATO analysts once doubted Soviet industry could produce reliably was machined in sufficient numbers to equip a fleet of over 400 aircraft. The aerodynamic performance targets set by the original military specification were met to a degree that forced a direct and measurable response from the world's most capable naval power. But looking at the broader strategic picture, critics have argued that the program also represented a massive misallocation of resources against a threat that existed primarily in the planning scenarios of the Soviet military staff, rather than in operational reality. The elaborate and expensive defensive system the United States built in direct response, the F-14, the AIM-54 Phoenix, the restructured carrier air wing, represented an enormous commitment of American defense spending driven specifically by the Tu-22M3's existence. The aircraft generated a defensive arms race it did not need to win. It merely needed to be plausible enough to force the expenditure. That outcome, an enormously costly strategic capability that achieved its purpose precisely by never being used, is the deepest irony embedded in the Tu-22M3's operational history. The bomber that the Pentagon once called impossible had successfully forced America to spend billions of dollars proving it could be stopped, while never once requiring that the answer actually be tested. The machine was never truly defeated in combat. It was simply outlived.